Okay, so welcome to the MKM321 2D FEM explanation video. So we're now going to go into the details of this finite element program, and you need to be able to drive this program. So what I would like you to do in parallel, because I know in W9L3V1 you are learning how to operate a package of finite elements. I think you're using FreeCAD and Calculix. I might be wrong, but that's how I understand what you are using at this stage, or using answers or some package, some CAE package to do finite elements. What I would like you to do is, the examples that you run in this course, is go and repeat them in that package and see for yourself that the answers are the same if you use the same elements. That's important. So I'm giving you a very basic 2D Python code, a code that you can open up, see how it works, see for yourself that it's really tangible, really doable. It's not that difficult, and it's essentially making sure that you understand that there's also needs for software that are used by engineers to actually be written by engineers. So there's definitely an industry behind this. There's a lot of engineers that do work in software companies. And we have to make sure that the software works for engineers and for design, etc. But more importantly, this is just to show you that you don't always have to pay millions of rands or hundred thousands of rands for a package. There are definitely options out there. And here's just to show you how simple it actually is to write a finite element program. Okay, so there's always three components to the finite element program. There's the pre-processing, where you set up the problem, and via that setup of the problem, usually if that problem then gets stored as an input file. Now lately in answers in those more recent packages, they may be saved as a project file, but it doesn't matter. It's a database, or whether it's a file, a text file. This one in this course will be a normal text file that you can open up with WordPad, Notepad, just a normal ASCII file. So that all that means is it's just text, okay, in a sort of Notepad environment. So that in the file type that we'll use here is always .inp input. These input files actually work in Calculix. So the files here should run also just as is in Calculix. Okay. So that's essentially the one aspect. The preprocessor, okay, defines the problem, constructing an input file. Then what happens is there's the solver part, and this is really what this FEM main program is all about. That FEM main program is really the solver, and the solver is usually the classical finite element solvers are from the 70s, like even Answers and a lot of these MSc, all of these finite element programs that we use now are. A lot of them are running on the solvers that came from the 70s, or written in Fortran. And Fortran is a programming language that stands for Formula Translation. It was designed to make computers accessible for scientists and engineers. So that's also quite funny. But a lot of these fancy packages that you buy essentially are still running those old solvers to a large extent. And the only thing that's changed is the GUI. The GUIs have become fancier, and maybe some extensions to the solvers and making it more general, etc., etc. But a lot of the work has gone into the GUI, translating CAD geometry to finite element geometry to finite elements, etc. So that's also important to understand that the solvers are often, in the finite element context, are quite old in most cases, and they were written. A lot of them were written a while ago. Okay, so the finite element solver is this FEM main program to a large extent that will then take an input file, and it will then solve the problem, and it will write then an output file, okay, and that output file will be the result that will be outputted. Okay, so that's essentially what that is about. Then yeah, so that's and then there's essentially the post-processing part, which is you take that output and then you sort of visualize and interpret the results. That's really what that boils down to. Okay, so this third point should maybe have been the not just returns the result, but yeah, so the returns for interpretation. It's that interpretation part and visualization and all that type of stuff. That's the post-processing. So there's always three steps: pre-process, solve, post-process. Done. You can check any of the CFD that you've done in MW323, any of the MKM that you've done, finite elements that you've done in 323. It's always got that. Let's pre-process, set up a problem, solve, wait a while, post-process, interpret. Okay, that's really the workflow. Okay, let's again. This is the steps that you would follow for a finite element program. But what I don't want you to forget is there's always that verification part. This interpretation implies verification, that you verified the answer as well. Okay, and it implies validation. that you are validating the answer. So this interpretation is not just looking at the pictures and say, oh, it looks nice and you're done. As an engineer, that means you verify, you trust the numbers, they are what they should be, okay, in the same ballparks, or you validate your finite element, say this model is appropriate for what I want to try and achieve. It relates to reality. That is critical to understand. This interpretation is not just willy-nilly looking at figures and be happy about that. It's verification and validation. It's critical interpretation, critical thinking, and making sure that you trust the answers. Okay, that is critical. Okay, there's no two ways about that. One thing that I want to just maybe highlight, if you do MRN next semester, if you do a finite element or any kind of CAE kind of simulation, you have to verify that with a sort of ballpark hand calculation. The finite element is not a way to circumvent a sanity check, okay? So whenever you do a CAE simulation in MRN, and especially if you end up with me with in MLX or in MRN, so let's consider MRX for instance. There's a lot of times MRN might not involve any of the simulation in my side. It's typically I do a lot of machine learning or generative models from data and stuff like that. That's sort of the focus area, or optimization. That is really my focus area for MRN. But for MRX, if you end up with me in MRX and you do a finite element simulation and you don't verify that with a sanity hand check, hand calculation, and say this is in the ballpark and I expect the answers and I trust the answers because they're in the right ballpark, you will be in trouble. Okay, you will be in trouble because it's non-negotiable. There is no way you do a finite element analysis and you haven't done a proper sanity check. That is not on. That is, then you're doing finite elements at the level of a high school kid, and that is inappropriate for a mechanical engineer, especially a third year, fourth year at the University of Pretoria. Okay, so I just wanted to rant about that you don't forget that this interpretation applies verification and validation. Okay, so inside the finite element program, so there's essentially, this finite element program is a module that contains lots of other things. So the one is Launch FEM. So the FEM program is sort of the solver, but it's actually just a module that contains a lot of utilities inside there. So the one is Launch FEM. So this actually, Launch FEM is actually the solver. Technically, the FEM main program, actually, I think I forgot that the fact is that this is just a module. We packaged it as a module a while ago. So I'm thinking of a different version. So the FEM program is just the module, pre-process, elements in post-process, and then there's FEM launch. This is the solver part. Okay, FEM launch. Okay, so just to take note of that correction that I'm just making here. Okay, so we launch FEM, and launch FEM takes essentially an input file. This string here is the name of the input file, so there has to be a file called q8_patch_translate.inp. Magnification factor, that's a magnification factors that we saw when we went through that Jupyter notebook on those plots. We can set that just to amplify the displacements. And then there's integration type, there's the full integration or reduced integration. We still haven't talked about the reduced integration, we'll still talk about that. But for now, full integration. Well, no, sorry, we have spoken about the full integration, reduced integration. The full integration is when I use the minimum number of Gauss coordinate points to fully integrate a undistorted element. Okay, and reduced integration is if I use one less. That's essentially what that boils down to. So this is the options that we have, Fi or Ri for that one. Okay, we haven't looked at the implication of reduced integration or anything, but we have spoken about it. Okay, so that's that. And then there's an output file that will be returned. There'll be some be a displacement vector for displacements. Okay, so that is essentially then the nodal displacements that we solved for. There's going to be reactions at those nodes. There's going to be meso stresses, stress along X, stress along Y, and shear stresses. So that is part of what we expect to see in the output side. Okay, so let's look at how a typical input file would look. So the input file structure would look as follows. Okay, it's just an ASCII file, but it would look as follows. There would be a star node. This is sort of the keyword to tell you, oh, this is now the node that we're going to define. So the node number, like we would have maybe node number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the X and Y coordinate of that node number. So this is the mesh that we're defining here, but not the elements, just the nodes that we're going to use in that mesh. This is what this node is defined. Okay. Then we have element type. Element type can be an even or an odd number. for plane stress or plane strain. That's so that's just how we decide on plane stress or plane strain, is by star element type and then following it by an integer. If it's 2, 4, 6, 8, it's plane stress. If it's odd, 1, 3, 5, whatever, then it's plane strain. So it's an awkward way of defining that, but that's the way it works. In this input file structure, star element, then we say element number, and then we say what nodes, and this is these node numbers that we've defined here. This is the order of the nodes to define a element. If I use 4 elements, I have a Q4, and I must number them anti-clockwise. So always anti-clockwise numbering, okay? And element number, if it's got 8 nodes, it's a Q8 element. Okay, so that's essentially that. That's also anti-clockwise numbering. And it must follow that node 5 is between node 1 and 2, node 6 between node 2 and 3, 7 between node 3 and 4, node 8 between node 4 and 1. It must follow that convention. Okay, that is important. Why does it follow this convention? Because it was coded with that assumption. And it was decided in the 70s by the researchers back then. This is the way we're going to standardize. Okay? It's not because it's the best or anything, it's just because that's what people decided on. So you have to understand that in life certain choices are driven by physics and mathematics, and some choices are just driven by the fact that there were many options and people standardized around something. Okay, but star boundary, so that essentially allows us to say what are the prescribed displacement boundary conditions, and for that we can have a node number. Okay, which is the node number that we want to have a prescribed displacement on. The direction, 1 for x, 2 for y. Okay, so it's a number followed by another number. This number direction can be a 1 or a 2 to indicate the x direction or the y direction. And the way you can remember it is 1 is odd, so that's x, 2 is y, it's an even, that is for the vertical displacement. And then the prescribed displacement value. Okay, so 0 implies it's fixed, but it can be positive or negative. You can say translate by -1, +1, 2, and the units will be implied by whatever Young's modulus and whatever these distances are. So there's no place here where you say I'm working in millimeters or anything. You take control of that by making sure when you put down your x and y coordinates, what is it going to be? Meters, millimeters. When you put down your Young's modulus, what is it going to be? Pascals, megapascals. Okay, that is, or gigapascals. You have to decide those things. Okay. And if you stuff up the units, your results will just be rubbish. Okay, so this is not, again, this is something, if you don't know what you're doing, then you are going to cause havoc. Star E modulus, this is just the Young's modulus for the material. Star Poisson is just the Poisson's ratio of material. Star thickness is just the constant thickness for them. Okay, so this is just constant thickness, we don't do anything else. And then star C load is for concentrated load. That's the node number, the direction 1 or 2, and the prescribed force. So if you want to do consistent node loads, you have to work out what those values are, how it distributes over the nodes, and then for each node set those values. This is how this input file works. Okay, this is important to understand. So here's an example input file for 2 Q8 elements. Nodes are numbered. So here's the node numbers. Here are the x and the y coordinates. Element type is 5. So remember, 5 means it's odd, it's plane strain. Okay. Then we have star element. So here's, why I say 2 Q8 elements? Anyway. Yes, this is actually 1 Q8 element. So here is 1 element, 1 to 8. Okay. Star boundary nodes, the node numbers. 1 for the x direction, 2 for the y direction, what the values are. Okay. Young's modulus, you ask yourself, what is this? Is this megapascal? Poisson's ratio, thickness, and the concentrated load. 10, 40, 10. Okay. It looks like 1/6, 1/6, 2/3. 2/3, 4/6. Okay, so that you can see sort of a distributed uniform load. You can already just by the numbers infer more or less. You visualize and infer what's chopping. Okay. So this is essentially how these things look. Okay. And then next up is the output file. So we have essentially first is the displacement array. So there's an array of the displacements, and this is now for the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16, yeah? Because it's a Q8 element. Well, I don't know why it's 2 Q8, sorry, this is just 1. But this is 1 Q8 element, and then essentially that is 2 degrees of freedom for the 8 nodes, 16 degrees of freedom for the element, and that's the 16 displacements for those places. What I know here is all the, so this is 1, 3, 5. I'm not talking about the index number, I'm just talking about the number from 1 to 16. 1, 3, 5, 7, 9, 11, 13, 15. Those are all the X displacement values, and all the even ones are going to be all the even ones are all the Y displacement values. Okay, the reaction forces, there's a matrix for the reaction forces that we have. Von Mises, this is the von Mises stress, and this is the stress at the nodes, okay, of the element. I think it's the nodes. Ooh, what is it again? Let's see if I can remember. I don't recall what we coded there. Is it the gas quadrature points, or was it actually at the? Let me just see, stress per element. I did do it at the node numbers, it seems, yeah. So at some point I had it at the integration point, and I think for this code I made it at the node numbers. The stress per element is reported at the 4 corners of the element. Okay, at first node, second node, third node, fourth node. Often in finite element packages it's reported at the gas quadrature points, but for simplicity I made it at the nodes so that you know exactly what they are at those nodes. Okay, so that is the stress at the nodes. Okay, reaction forces. You can now just you can read through this and see for yourself what the reaction forces are about. But the reaction forces here, to interpret them, because remember they just popped out here as a matrix, so what are they relating to? I want to show you now by saying the boundary nodes, the order in which you specify these boundary prescribed displacements, this is the same order as the reactions. So this will be for node 1 x direction 0, this is the reaction force at that node. So this is node 1 x direction, this is node 1 y direction, this is node 1 y direction, this is node 4 x direction, this is node 8 x direction, and you can see here that 8 is in the middle on this edge, and then essentially 1 and 4 is this 2 at the edges. Look at that, minus 10, minus 40, minus 10. What was the load that I applied? The load that I was applied was 10, 40, 10. For the mid side 40, 10, 10 for the edges, and we can see here the same. So that everything looks hunky-dory in equilibrium. Minus 10 for the outside, and minus 40 for the mid side node. Beautiful, okay? And if you were to change the order of these things, the order here would also change. So bear in mind, the reactions are specified by the order of the boundaries. Okay, let me see what the time is. If I should, it's almost time to stop. So there's essentially, you can just interpret that. What is important here now is, and this also holds for you this, and this is the force and moment equilibrium, must hold, okay? Remember what I told you, we're solving we're approximating, so the solution that we get is an approximate solution for the complex problem by solving a simpler problem exactly. So in this simpler problem is nodal force equilibrium. So at each node must be in equilibrium, yeah? That's the sum of the forces, that's where the KQ equals F system that we solve. And at the end of it, that system, in terms of nodal equilibrium, what I mean is nodal equilibrium, sum of forces in X, sum of forces in Y, and any of the moments, depending on whether it's a 2D or 3D problem, all of those equilibrium equations must be satisfied, okay? And we can see that they are satisfied. So both force and moment equilibrium, this is critical, and you have to be able to verify that, okay? This is important, that the nodal force equilibrium must hold. So sum of force in the X direction, sum of force in the Y, and sum of the moments around any point must always be equal to 0 for a static problem, okay? So this is important. So sum of force in the reaction forces in the X direction and the applied forces. So let's just look at the reaction forces in the X direction, minus 10, minus 10, minus 40, that's minus 60. It's applied force in the X direction, it's also 60. Those to cancel out. So the sum of the X direction is exactly minus 60. If you do sum of directions, sum of forces in the Y direction, and sum of moments, you'll see everything is hunky-dory, okay? Because each of these, this 10 and this 10 and this 10 and this 10 and this 40 and this 40, they all follow in the same line. So for moment equilibrium is also satisfied. But this is really important to understand. Force and moment equilibrium must hold. The book doesn't emphasize this, but I emphasize it, and you have to be able to check it. This is critical and important for this course. Okay, that's about it for the manual. So hopefully this gives you a good idea of what it's all about. And the manual, you'll always have it available. You don't have to memorize anything of this. It'll always be up hand during the test and exam. You'll always be able to access it as part of the material. Okay.